Ladies and gentlemen, welcome to the session 1.2 to 1.5. My name is Miloš Milošević. I will be chairman of this session. According to the rules, each presentation has 15 minutes and discussion will be on the end of the session. So we will start with Mr. Irfan Habib, please, who will present the paper titled An Experimental Study on Crack Hole Interaction Under Dynamic Loads. Please, Mr. Habib, take your time. It is already.
Good afternoon. I'm Irfan. Today I'm going to talk about an experimental study conducted to observe the crack dynamic fracture and how it is influenced by the voids in brittle materials. So when it comes to dynamic fracture of brittle materials, heterogeneity has a large influence, and that leads to changes in the crack propagation velocity changes and direction of the crack path, and so basically that affects the design parameters. And studies have been conducted for decades, and there are still areas which are uncovered because of the complexity of the system. So here I have conducted an experiment to observe how crack interacts with the voids as a subset of the heterogeneity. So in the specimen, cylindrical voids are introduced and observe how dynamic fracture behaves because of the voids. And this project is funded by outcome project from European Union's Horizon 2020 program. So I have considered this specimen, reverse tapered triangular specimen. This is chosen because of the geometry mainly. Load is being applied from this direction, and since the area in this direction is completely touching with the load, so this is appropriate for the loading conditions, and I have used this specimen to avoid fracture at the edges. For example, if I were to use this, I would be having fracture in these two edges. And another plus point of this is to observe the crack path in that direction, since instead of 3-point bending specimens, this has higher length in that direction, and it helps to observe the crack path during the fracture. So here I have considered mainly 3 sets of specimens. One with 2 mm radius, this is considered as reference, and in second case, symmetric void of radius 1 mm, and that is to observe the variations of radius, how void radius affects the dynamic fracture. And the third case, there is an offset of 1 mm, that is to observe the effects of location of the void. So to apply the loading, I have used Hopkins and bar. So how it works is that there is a pressurized gas in the cylinder, and when the valve is open, the striker accelerates and hits the instant valve. And it creates a stress wave which passes through the instant valve and applies the loading to the specimen. And on the way, it triggers the camera, high-speed camera, which takes the images during the fracture. So the camera used for this takes 180 frames with a pixel size of 972 by 768. And for most of the cases, I have used 1.5 million frames per second. And from the images obtained from the high-speed camera, the digital image correlation is used to find the displacement field and further analysis. And to get the fracture parameters from the DIC, I have developed a program. So what it does is that from DIC we get the displacement field, and this program looks around the domain and finds a crack tip and appropriate stress intensity factor. It maps the linear elastic crack tip field and compares with the experimental field, and looking at the error distribution and gradients of the error distribution, it finds the crack tip, and corresponding stress intensity factor is taken for the further calculations. And I did this for the whole experiments, and so if once we do that, we get crack tip for each instant. In result, that is the velocity once we know the time frame between two frames. So this is from one test, and crack path is shown. So all this analysis has been carried out in Fourier space to reduce the noise. So to talk about the results, as I mentioned before, there are 3 cases with 3 specimens each, and striker velocity varies from striker velocity. So striker velocity varies from 19 to 20 meter per second, which is controlled by the pressure in the gas cylinder of Hawkinson bar, as I mentioned before. And 3 configurations for extra specimens: stress intensity factor, crack propagation velocity, and crack arrest time in the void. So this is the crack path from one of the experiments. Crack goes into the void. Depending on the specimen, it stays there for some time, then comes out. So here I have measured the time it spends inside the void and the emerging angle also. And this is from one of the experiments. This is the lateral displacement during the fracture. So out of 3 cases, this is the first one, and this is considered as a reference one with the void of radius 2. So stress intensity factor, there is a large margin of critical stress intensity factor is scattered. That's because of the highly sensitive nature of the sharp notch introduced. And these variations are due to the changes in the dynamic loading from the Hawkinson bar. And this is the crack propagation velocity. As you can see, there is a general trend of velocity is increasing as it approaches the void. And average time, average crack arrest time in all these 3 cases is 23.3 microseconds. So when it comes to second case of radius 1 mm, initial critical stress intensity factor is not as scattered as set 1, but velocity increment is lesser compared to the previous case. And crack arrest time is 7.3 here, almost 1/3 of the previous case. That is because of the reduction in radius, and instant stress field around the void, and kinetic energy. Incoming crack propagation velocity also has an effect on this parameter, on crack arrest time. And in the third case, with an offset of 1 mm with radius 2 mm, critical statistic factor is almost in a small margin. Actually, this scattering is mainly due to the distortion happens to the incoming stress wave because of the void in the domain. So when there is an offset, that interaction is very less, and it doesn't distort the wavefront so much. That's why stress intensity factor is almost in a small margin. And the velocity increment is highest in this case compared to the rest of it. And crack arrest time here is slightly higher than that of the case 1. It shows the capacity of the void with an offset that it can carry slightly more load, or it can hold the stress for some more time. And to validate some of the observations, I ran some simulations. So here there is a sharp notch and a void of radius 2 mm at a distance of d. So I considered 4 cases, 1 without any void, and rest of the 3 with 3 different distances. So this was to observe how stress field varies near the sharp notch depending on this distance d. So as you can see here, d equal to, when the distance is low, lateral stress is the highest. So that is due to the deformation of the wavefront and less material as the void is getting closer to the notch. And the crack emerging angle is the second parameter we considered. And for this, I ran simulations, and the crack has entered the void. Then looked at the emerging angle, and with experiments it shows a pretty good match. And further on this, I'm working with mode 1, mode 2 interactions and crack deflections, and in parallel trying to develop a better code for crack propagation. That's all.
Thank you very much, Mr. Ifran.